Today we're going to be starting section 8.3 and we're going to be looking at radicals and simple radical form. This is going to build upon those exponent rules we learned way back in chapter 6. So what I want you to do is remember that when we are looking at a root, we can always convert it into an exponential form, and our rules are going to be very simple. For example, if I take the third root of 128, that can be rewritten as 128 to the 1/3 power. And so taking roots is just a form of exponentiation, and the properties of exponentiation automatically apply to radicals. So let's review those root of a product and root of a quotient rules. So first, the root of a product. In radical form, the nth root of a times b is the same thing as taking the nth root of a times the nth root of b. And in exponential form, that rule looks like this. A times b raised to the 1 over nth power is equal to a to 1 over nth times b to 1 over nth. And so those rules we've already seen this year, only it's going to look a little bit different in radical form. And so the next one we're going to review is the root of a quotient where b cannot equal 0. And so in radical form, we would take the nth root of a divided by b, and that's the same thing as taking the nth root of a all over the nth root of b. And in exponential form, that rule looks like this. A over b all raised to the 1 over nth power is equal to a to the 1/nth all over b to the 1/nth. And so these rules apply to non-negative values of a and b. So let's look at a couple of the easy simplifying problems. So if you are asked to simplify the square root of 288, that would be the same thing as saying, well, I know this is equal to 4 times 9 times 2. This is a skill we've already visited this year. And looking at that, I know that 4 and 9 are perfect squares. So this ends up being the square root of 4 times 9, all times the square root of 2. And those square roots are 2 times 2 times 3 times radical 3. And when this is simplified, it's simplified into 12 times the square root of 2. And the reason why the expression 12 times the square root of 2 is considered simpler is because the radicand is smaller. And if you would put this into your calculator and do a quick check, which I'm going to write over here, in the calculator, the square root of 288 is equal to 16.97, blah, 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 blah. And 12 times the radical 2 is also equal to 16.97, yada, yada, yada. And so this is the simplified form of the square root of 288 because that radicand is smaller. Let's look at another example. Another simple example would be if I'm asked to find the square root of 128. Looking at that value, I know 128 is 64 times 2. And 64 times 2 is 8 squared. So this becomes the square root of 8 squared times 2, which is 8 squared is 64. Then I have the square root of 8 squared times radical 2. And that ends up being 8 times radical 2. And for those of you that are confused where that 8 squared came from, that's going to be 64. Let's do one more simple example before we dive into the algebra 2. And so looking at this one, we're going to take that square root of 128 plus the square root of 18. we already figured out that the square root of 128 is equivalent to 8 radical 2. And 18 is a very small number, and we know 2 times 9 is 18, and the square root of 9 is 3, so this becomes 3 times radical 2. And because I have the same radicals, those two values can be added together, and this ends up being 11 times the radical of 2. So those first 3 examples are simple ones that you might have seen in Algebra 1. So now let's go ahead and dive into a couple of the rules in Algebra 2. So one of the first things we're going to look at is rationalizing the denominator. Radicals in the denominator can cause major issues in math. So we always want to rationalize that denominator if we need to. And we're going to do that by multiplying that denominator radicand by a perfect cube. So for this example, I have 1 all over the cubed root of 2. So for this, I need to multiply. I'm going to rewrite. And then I need to multiply both the numerator and the denominator by a perfect cube. And a perfect cube in this case is going to be the cubed root of 4 all over the cubed root of 4. And so 1 times the cubed root of 4 becomes the cubed root of 3 all over 4. And the cubed root of 2 times the cubed root of 4 is going to be the cubed root of 8. And so we can go ahead and simplify this. The cubed root of 8 is 2. And so we can go ahead and this will become the cubed root of 3 over 4. The cubed root of 3 of 4 all over 2. Now, we can go ahead and do a calculator check on both this value and this value. And in the calculator, both will come out to be 0.79370. The next type of problem that we're going to see is looking at a fractional exponent, something we are very familiar with in our course. And so if we are asked to simplify the 8th root of 64, the 8th root of 64 can be rewritten as 64 to the 1/8 power. That is our fractional exponent definition that we learned back in chapter 6. 64 is 2 to the 6th power. So we can rewrite 64 as 2 to the 6th, all raised to the 1/8 power. And so, if we want to simplify this, power to a power rule, this becomes 2 to the 6/8 power. 6 times 6 to the 1/8 is just 2 to the 6th raised to the 1/8 power is going to become 2 to the 6/8 power, which can be reduced to 2 to the 3/4 power. And then we can rewrite this in radical form, a skill we've already learned in chapter 6. And to rewrite this, it's going to look like the 4th root of 2 to the 3rd, which we know is 8. So this then can be written as the 4th root of 8. So the 4th root of 8 and the 8th root of 64, when put into a calculator, will come out as 1.6817. So this value is the simplified version of our example. There are 3 rules that you need to remember when we are trying to do simple radical form. And those rules are: the nth root contains no nth powers as factors. The root index must be as low as possible, and there could be no radicals in the denominator. So, let's look at a version that looks like this, where we need to use a conjugate. So for this example, if I have 2 all over 5 plus radical 3, and I need to simplify this problem, I need to use the multiplicative identity, which is the conjugate. So for this, I'm going to multiply the numerator and the denominator by the conjugate, which is 5 minus radical 3 all over 5 minus radical 3. This is a conjugate. That's an old rule coming back to play. And when we go ahead and multiply the conjugate binomials, we end up with 2 times 5 minus radical 3 all over 5 squared minus radical 3 squared. All I've done is multiply across. And so now, in the next step, I can go ahead and do some simple math. And when I do that simple math, this ends up as 2 times 5 minus the radical 3 all over 25 minus 3. The square root of 3 squared eliminates that square root. So now I can continue some simple math. I have 2 times 5 minus radical 3 all over 22. And when I go ahead, I can simplify this because 2 and 22 are simplified. So 2 goes into 22 one time, so I'm left here with 11. So then my final simplified version of this is 5 minus the radical 3 all over 11. And so this simple arithmetic, when placed into a calculator, 5 minus radical 3 all over 11 is going to give me the same decimal that 2 all over 5 plus the radical 3 gives inside of a calculator. And that decimal is going to be 0.297, yada, yada, yada. So, these 4 different types of problems that we see, some of them may be familiar, some of them may not. And so what we're going to do today is look at a homework packet before we do some of the more challenging problems. So I'd like you to watch the next video of me explaining some of these types of problems in your homework packet.